Hi everybody, welcome back. This is the second in a series of videos that are out this week for you to learn a little bit about molarity, mole conversions, and then next video we're going to talk about something called stoichiometry, but this video is all about molarity, so let's get started. The first question, of course, is what is molarity? Well, molarity has a lot to do with concentration, and we know that concentration of a solution has to do with how much stuff is dissolved in the liquid. So the technical terms for that are the solute. The solute is the thing that is dissolved, and the solvent, that's the liquid that does the dissolving. So if we had a solution of salt water, the salt would be the solute, and the water would be the solvent. Now, obviously, we understand that you can have different concentrations of salt water. Obviously, the ocean has different concentrations of salt depending on where in the world you are, right? The Dead Sea has so much salt in it that you could float on it for hours and it's like you're taking a bath. Like it's the weirdest situation, but you know, the ocean in the Gulf of Mexico, that's totally different. You can't float for hours. There's way less concentration of salt. If you haven't been to the ocean, well, we can just talk about concentration with Kool-Aid. Hopefully you guys have all had Kool-Aid. If not, I don't know what you're doing with your life. Please find a way to go to Walmart and buy a 20-cent pack of Kool-Aid like immediately. So if you want really flavorful Kool-Aid, you might have put 2 packages of Kool-Aid mix into 1 pitcher of water. That makes it more concentrated than if you had just 1 pack of Kool-Aid mix in the normal amount of water. Okay, so concentration has to do with how much solute, that's the stuff that's dissolved, is in the solvent. Oh, there's my example about the ocean. So next, the chemistry term for concentration is molarity. So in this context, concentration and molarity are going to mean pretty much the same thing, except molarity has to do with the number of moles in 1 liter of total solution. So instead of how much stuff, we're going to get more specific here. In chemistry, we use moles. So molarity is the number of moles in 1 liter of solution. So that looks like on the left over here, we've got big M is the symbol for molarity, big M. And then we have the number of moles on top, and then on the bottom, we have 1 liter of solution. So if you're thinking about how you're going to write this for units, it would just be moles over liters, and then you would have some number that goes right here. And then here's just a visual for you. We've got that high concentration or high molarity on the left, right? You see we have a lot of particles. And then on the right, we have way fewer particles. So this is a lower molarity. Of course, we're not going to be just using particles. We're going to be talking about moles. But there's a great visual for you. Obviously, if we have more particles, we have more moles, which is a conversion that we learned about in the last video and even last semester. So make sure you're not forgetting all those good conversions that we've talked about. So let's see how we can calculate molarity. My first question here says, what is the molarity of a solution containing 0.75 moles of KCl in 45 milliliters of total solution? So I know how many moles I have, and I have milliliters. Now, molarity is moles divided by liters. I can see that I have the moles, but I don't have liters yet because this is in milliliters. So first I need to convert my 45 milliliters into liters. Hopefully you remember how to do metric conversions. We talked about these last semester, right? Milliliters on the bottom, liters on the top. There are 1,000 milliliters in every 1 liter. So I have 0.045 liters of solution. Now that I know that, I can go back to my equation. Molarity is moles, 0.75 moles, divided by the liters of solution, which I just found 0.045 liters. I can plug that into my calculator, and you get 16.67 molar. That's how we say that, 16.67 molar. If we want to use sig figs, then the answer would be 17 molar. And that's how we use the formula for molarity. That's how we calculate it. Let's do another one. In this example, I have grams and liters. So it says, what is the molarity of a solution containing 185 grams of NaBr, which is called sodium bromide, in 2.4 liters of total solution? So if I'm thinking about molarity, molarity is moles over liters. Before I can do anything with that molarity, I do have my liters, but I'm going to have to convert my grams into moles. So good thing we just reviewed that, right? 185 grams. We're going to convert that to moles. And we are going to have to find the molar mass. Right? Molar mass is the mass of the constituent pieces. So the mass of sodium is 22.99. The mass of bromine, 79.90. Then you add those up and it gives you a molar mass of 102.89. We take that number, we plug it in on our conversion, 102.89. And now we can determine how many moles of sodium bromide we have. Looks like we have 1.80, that's with sig figs, 1.80 moles of sodium bromide. I wish we could be done there, but remember, this is just the moles, and I wanted to find molarity. So to find molarity, where's my arrow? To find the molarity, we need to take those moles that we just found, 1.80 moles, divided by the liters, 2.4 liters. That gives us a molarity of, with sig figs, 0.75 molar. That is not very strong. I will say the 17 molar, that's the type of stuff that will, if you have 17 molar hydrochloric acid, that's the type of stuff that'll burn your skin off. A 0.75 molar concentration is not very concentrated. This is more something used in the lab totally safely. Now we know how to calculate molarity. How can we use this calculation to help us with the rest of our conversions? If you don't have your mole map out, go ahead and get it out. We are going to start talking about this last component, right? In the last video, we talked about molar volume of gases. We talked about Avogadro's number. We talked about molar mass. Today, we are going to talk about molarity and how that plays into all of our conversions. Just like we used molar mass to convert between moles and grams, we can use molarity to convert between moles and liters. But you have to be careful. Right? You'll notice that liters is on both sides of this mole map, or it's in two places. We've got liters on the top left, and we've got liters on the bottom right. This we have to be careful because on the top left, this is when we have gases. On the bottom right, that's when we have a liquid. Right? Only works if we have liquids or solutions. So be careful that you're using the correct conversion factors. We'll go through some examples and I'll show you that it's fairly straightforward. So first calculation says how many grams of NaOH, which is called sodium hydroxide, is in 0.050 liters of 3.0 molar NaOH. Oh, and the problem was so kind and gave us the molar mass of sodium hydroxide. But let's break down this problem. The first thing that I want you to do, anytime that you see that big M for molar, I want you to rewrite it into moles over liters. That's going to help you see that this value is a conversion factor, and you can use it as a conversion factor. Okay. So then what you see is we have liters, we have moles over liters. I'm going to solve for grams, question mark. Okay, let's look at our mole map. I know that I would need to end up in grams, okay? Which means the only way I can get to grams is by going through moles. If I'm in moles, oh, look, this is, if I can go from over here, from the volume, so from my 0.05 liters, I can convert that to moles using my molarity, and then go from moles to grams using the molar mass. So that's our game plan here. We're going to go from volume to moles and then to grams. So let's set up the skeleton for this conversion. I'm going to start with the volume. And that's where I said I was going to start. So 0.050 liters. I'm going to convert liters. Instead of liters again, I'm going to go on the bottom. My second step is moles. So moles goes on the top. And then I said after I got to moles, I wanted to convert moles into grams. So this is my skeleton for how I'm going to solve for grams. Once you have that skeleton set up, we can go ahead and plug in all of the conversion factors. Our first conversion factor has moles over liters. And wow, since we had already simplified our molarity thing earlier, we can see that there are 3.0 moles in 1 liter. It will always be 1 liter on the bottom. And that second conversion factor, grams and moles, we already know that that means molar mass, and the problem gave it to us, so I'm just going to plug in 40.00 grams, and that's in 1 mole. So now I have all my conversion factors plugged in. I just need to calculate this out. So we're going to multiply across the top, divide by anything in the bottom. So our final answer is going to be 6 grams. But how do I appropriately show sig figs? 6 just has 1 sig fig. I need to show 2 sig figs. So we have to add a 0. 6.0 grams is my final answer. Let's do another problem. Again, you are going to want to keep that mole map out. It's going to be so helpful for you. I unfortunately have to scroll down and get rid of mine. Tragic. So make sure that you have yours so that you can compare. In this problem, it says we have 113 moles of HCl for a reaction, and I want to know how many milliliters of 1.5 molar hydrochloric acid I would use. Okay, again, I have a lot of information. Let's break this down. So I have 0.113 moles of hydrochloric acid. I'm going to find milliliters. And another thing that I know is the molarity. Remember, as soon as you see that molarity, I want you to break it down. So we've got 1.5 moles of HCl per liter, okay, in every 1 liter. So looks like I have moles. I need to get to volume. If we are looking at the mole map, moles is in the middle, volume is down here. So it looks like I need to go from the middle to volume, which means I'm going to start with moles. I'm going to start with 0.113 moles of HCl. Just planning my attack here. I'm going to go from moles, which means moles is on the bottom, to liters on the top. But I actually need to be in milliliters, so let's add another step here. Liters is on the bottom and milliliters is going to go on the top. Now let's fill in those conversion factors. This time you see that the molarity is upside down. Liters is on the top, moles is on the bottom. That is okay. As long as we keep the 1.5 with the moles and the 1 with the liters, it does not matter. Then to convert milliliters and liters, we remember there are 1,000 milliliters in 1 liter. To solve, multiply across the top, divide by everything that's on the bottom. When you do that, you get an answer of 75.3 milliliters. And that's how many milliliters of hydrochloric acid it would take for my reaction, whatever that reaction is. Let's do another one. It says I have a lab experiment that required 44.8 milliliters of a 0.25 molar calcium hydroxide solution. How many grams of calcium hydroxide were used? Let's break this down. So my given of my 44.8 milliliters, I also see that I have 0.25 molar. Oh, it says molarity. I'm going to just rewrite that really quick. 0.25 moles over liters. Then I am being asked to find the grams. All right, so I need to get to grams. I know that grams is in the bottom left of my mole map. Moles is in the middle. Volume is in the bottom right. So I'm going to have to do a couple of steps here. If I need to get to grams, I have to start in liters. But I have milliliters. So 8 milliliters. Before I even do anything, I have to at 2 liters. Milliliters. Liters. I'm just going to go ahead and keep stringing this skeleton along. Once I'm in liters, I have to convert to moles. Liters on the bottom, moles on the top. And then once I'm in moles, I need to get to grams. So moles on the bottom, grams on the top, and that will hopefully give me my final answer, grams of calcium hydroxide. Now let's take a look at our conversion factors. Okay, we got a lot going on. Very easy, it's just a metric conversion. So 1 liter, that's 1,000 milliliters. Second conversion factor is molarity. You've got moles and liters, so I put that 0.25 moles over 1 liter. Last conversion factor is our good friend molar mass, so it seems like we are going to have to calculate that. Total, my molar mass is 74.1. And that just goes right into my conversion factor there. And we've got everything all set up, so now we solve, multiply across the top, divide by anything that's in the bottom, and your final answer for grams of calcium hydroxide is 0.830 with correct sig figs. I've got one more problem for you guys. On this one, I want to see if you guys can solve this on your own, so go ahead and pause the video, and then I'm going to show all the work, and then you just need to see if your answer matches mine. Hopefully you got this far with your setup. Now to solve, we just multiply across the top, and our final answer with correct sig figs is 7.1 times 10 to the 23rd particles of MgCl2. I hope these conversions were fairly straightforward for you. If you want to go back through the video, rewatch any segments, I highly recommend it. But from this point, you now know how to do all of the conversions. If you're looking at that mole map, you can do every single one now. Right? We learned molarity today. So you should be good to go ahead and work through the worksheet on all mole conversions. And I'll see you next time. And we're going to start talking about stoichiometry.